Hello, everyone. Today we're going to be presenting parallel complexity theory. Next slide, please. To start off, classic complexity theory gives us tools like P and NP to measure how hard problems are on a single machine. But modern computing is deeply parallel, from multi-core CPUs to massive distributed clusters. Parallel complexity asks a different question. Which problems can we actually speed up by throwing more processors at them? The key insight is that parallelism introduces two separate costs: how many synchronized steps we need, and how much total work all processors do combined. The class NC is our formal answer to what's efficiently parallelizable, and that's what we'll dig into. Next slide, please.
Yeah, so there are multiple models of parallel computation, and in this presentation, due to time constraints, we'll look at three broad models, like broadly studied models of parallel computation. All three models need to answer two main questions, which is how much parallel time is needed and how much work is needed. And the first model that we'll be looking at is the circuit model of parallelism. Uh, in this case, as we studied in class, this uses the circuit model of computation represented as a DAG, where uh, each uh, where each node is basically a logic gate, and the size of the DAG is basically the number of gates needed to realize a circuit, and the depth is the longest path from the input to the output. And the basic fundamental idea of the circuit model of parallelism is that the gates in each depth can be evaluated in parallel. So the depth essentially measures the number of parallel steps, and the size measures the total amount of work. Next slide, please. The circuit model of parallelism, like one example for that is the Bose-Nelson sorting problem. This basically asks for a fixed sequence of compare and swap operations that sorts n inputs. And the network in this case is divided vertically, with each level having one or more comparators between participating channels. In the figure, you can see like in level one, X1 and X2 has a comparator between them. So there's a horizontal line connecting them both. And in the on the side of the output, the left channel of the output basically has the minimum, and the right channel has the maximum of the two operators. So in this case, in level one, you can see that x1, the maximum of x1 and x2 goes to the second channel, and the minimum goes to the first channel, and the maximum of x3 and x4 goes to the fourth channel, and the minimum of x3 and x4 goes to the third channel. And by the end of level two, uh, the first channel has the minimum of all four inputs, and the uh, fourth channel has the maximum of all four inputs. So in level three, you do a compare and swap between the second and third channel, and in the end, you get a depth three and size five circuit for sorting four inputs. Next slide, please. Yeah, the second model of parallel computation is PRAM, parallel random access memory. In this, the model basically consists of multiple processors, each of which can perform a local computation in the same synchronized time step. The one key aspect of this is that all processors share one single shared global memory, and in one parallel step, each processor can either read from memory, do some local computations, or write back to memory. The main complexity measures for this form of parallel computation is parallel time and work, which is the number of synchronized steps and the total number of processor operations. Next slide, please. So there are multiple variants of parallel random access memory based on which are organized based on how they handle simultaneous memory accesses. The first one is exclusive read, exclusive writes. This basically means that no two processors may read from or write to the same memory cell at the same time. This is possibly the most restrictive variant, but it's also the easiest to relate to like realistic contention-free parallelism. A typical scenario in which this is used is when you want strong theoretical guarantees, and you want to avoid any sort of contention, or when you want more robustness, and when you want to prove your results essentially in the strictest of constraints. The second subvariant is concurrent read exclusive writes. In this, many processors can read from the same memory cell simultaneously, but the model still forbids simultaneous writes to the same cell. This is easier to program. Typical algorithm, parallel algorithms use concurrent read and exclusive writes. Most graph algorithms, for example, use this. And the final, most powerful subvariant would be concurrent reads and concurrent writes. This allows multiple processes to read and write the same cell simultaneously. And since they can sometimes conflict, um, variants of this also specify how conflicts are resolved. For example, you can choose an arbitrary writer if there are conflicts, or you can choose you can basically use a priority based selection. This is typically used when you want to design the fastest possible algorithm, and if you're looking at upper bounds of theoretical complexity. The figure here has um, an algorithm to parallelly add 8 numbers organized as a binary tree with two input adders. As you can see, the this algorithm needs overflog and parallel time and is linear in the number of processors. Yeah. Next slide, please. Yeah. So next we're looking at the parallel computation thesis. The thesis basically states that for most reasonable models of parallel computation, the amount of parallel time needed to solve it should be polynomially related to the amount of sequential space. And this is just a different this basically says that parallel computation is just a different way of organizing computation, and it should still have some sort of mapping to classical complexity theory. And next slide, please. Yeah, this brings us to the third and final model of parallel computation, which is bulk synchronous parallelism. In this model, all computation is assigned to processors, and it proceeds in repeated super steps. And all super steps have three parts. The first part is local computation on each processor's private data, and then the next phase would be communication among different processors, and then the last step would be bulk synchronization. The idea is that parallel algorithms should be analyzed not only by how much work they do, but also by how often they need to communicate and synchronize. Most machine learning workloads and systems for machine learning workloads use this type of parallelism. And these are the three models. Next slide, please. Yeah, to summarize, um, most of this was covered in the previous slides, but the main idea that I want to draw attention to is that the use of each model is based on what you want to use, what you want to study. So in the case of the circuit model, you want to mainly study complexity theory and basically study NC circuits. And then in PRAM, you use it for algorithmic design, and then for PSP, you basically want to look at how you deploy these models and how you would actually realize them in real life. Yeah. Next slide.
Yeah. Before diving into NC itself, it's worth grounding why we care. We know NC sits inside P. Anything with a fast parallel algorithm also has a polynomial sequential algorithm. But the reverse is the deep open question. If P equals NC, then every problem with an efficient sequential solution can be parallelized efficiently. Most researchers believe this is false, that some problems have unavoidable sequential dependencies, but we can't prove it yet. This question motivates everything in the field. Next slide, please. NC has two equivalent formal definitions, and understanding both is useful. From the circuit side, we think of a problem as being computed by a family of Boolean circuits, one per input length, where the depth is polylogarithmic and the size is polynomial. From the algorithmic side, we use the PRAM model, where many processors share memory and take synchronized steps. The beautiful insight here is that depth and parallel time are the same thing. If we can evaluate different levels of the circuit simultaneously, depth is exactly how many rounds of parallel computation we need. Next slide, please. NC isn't monolithic. It has an internal hierarchy based on how much depth you're allowed. NC0 is extremely weak. Constant depth means each output bit can only see a constant number of input bits. NC1 allows logarithmic depth and can already do surprisingly rich things like evaluate Boolean formulas. NC2 and beyond handle more complex algebraic and graph problems. The hierarchy also connects naturally to space complexity. L and NL sit neatly between NC1 and NC2, which shows how circuit depth and sequential memory are deeply related resources. A great concrete example of NC in action is parallel prefix computation. The tasks sound sequential; each prefix depends on the one before it. But Ladner and Fisher showed you can restructure this using a tree of associative operations, cutting the depth of O of n log n. This is a template for a huge class of parallel algorithms. Whenever you have an associative operation applied sequentially, you can often parallelize it with a binary tree structure. It also illustrates the work depth trade-off. The parallel versions the parallel version does more total work than the sequential one, but it finishes much faster. Next slide, please.
Okay, so let's look at a parallel algorithm in action. So the algorithm that we're going to look at is Chunky's algorithm for matrix inversion. This basically shows that this algorithm shows that matrix inversion is an NC, and it gives a parallel algorithm for that. Classical Gaussian elimination takes of n cube sequential time, and we're going to study this algorithm sequentially. We're going to start with simpler parallel algorithms for smaller linear algebraic problems, and then slowly build up to Chunky's algorithm. Next slide, please. Yeah. First off, we look at a parallel algorithm for vector dot product. So if you want to compute A dot B, you basically compute all individual components as products in parallel, and then you just sum them up using the parallel algorithm that we saw earlier, which organizes adders as a binary tree. So this takes logarithmic parallel time and linear in the number of processors required. And then parallel matrix multiplication extends the vector dot product algorithm. So for each of the n cross n, I mean n times n elements, it uses the parallel vector dot product algorithm. So this takes O of log n parallel time and uses O of n cube processors. And then to compute the parts of a matrix, we use binary exponentiation. So if you want to compute a power 16, let's say, you just keep squaring till you reach a power 16. So this takes of log k times log n, and with n power 4 number of processors. In our case, we will end up having to calculate all parts of the matrix up to from 1 to n. So the total time complexity will be of log square n. So everything is going to be polylogarithmic. Next slide, please. Yeah. The next parallel algorithm that we look at is inversion of a lower triangular matrix. So it's known that any lower triangular matrix can be represented as a block in the way that's that in the slide, and then its inverse can be computed again in a lower triangular matrix format in the following block. So we come up with a divide and conquer algorithm where you invert B and D recursively in parallel. And then once you've inverted them, you do two matrix multiplications to get the off diagonal block. Uh, Assume that, let's say that T of n is the time complexity for lower triangular matrix inversion. We get a recursive definition for the time complexity as T of n is T of n over 2 plus 2 times m of n over 2, where m is basically matrix multiplication, like the time complexity for matrix multiplication. We know that m of n takes O of log n, so T of n takes O of log square n time, and it's polynomial in the number of processors required. Next slide, please. Yeah, next we're looking at parallel linear recurrence. The matrix form of linear recurrence is I minus S times X equals C. And in this case, I minus S is lower triangular. And we use, again, the lower triangular matrix inversion to calculate X. And this takes O of log square n time and polynomial number of processors. Next slide, please. Yeah, the next setup algorithm that we'll be looking at is finding the characteristic polynomial of a matrix. Um, so as the slide says, there's a way you can represent the characteristic polynomial as a recurrence relation. So you basically take that and you compute the trace of different parts of the matrix, and then use that to solve the recurrence. And this again is polylogarithmic time, and then linear, not linear, sorry, polynomial in the number of processors required. Next slide. So now that we've looked at all the basic setup needed for Chunky's matrix inversion algorithm. Uh, let's come to the algorithm itself. We use the Cayley-Hamilton theorem, which states that every square matrix must satisfy its own characteristic equation. So based on that, we get the following um, equation to calculate A inverse. So the algorithm proceeds as follows. You just compute all powers of A in parallel, and then you compute all the S sub i's based on the linear recurrence algorithm, and then you finally evaluate the equation to get A inverse. So the final algorithm takes polylogarithmic time and then polynomial in number of processors. Next slide.
Um, so now we're going to talk about constant depth circuits. Um, so for, as we previously saw, we talked about NC, which contains polylog depth circuits. So the question is, it seems like we can do a lot with just like NC1 and NC2. How much can we do with NC0? And this turns out to be pretty interesting because a lot of these circuit classes are extremely weak up until we hit ACC0. So let's go through this. So NC0 has bounded fan-in, but AC0 does not. And so these are circuits which get and OR gates and have constant depth. So if we have bounded fan-in and constant depth, we can't compute and over all inputs for sufficiently large inputs. So that gives us a separation between NC0 and AC0. And then the question is, what happens if we give our circuits a more powerful kind of gate? So AC0P gives AC0 circuits the ability to use mod P gates for prime P. So it just tallies the number of inputs and gives the modulus relative to P. Or sorry, it gives if it is 0 mod P. And AC0 is separated from AC0P by exactly that problem, mod P. And the proof of this is shown by Razborov. The P equals 2 case that mod 2 is not in AC0 is shown by Hastad since mod 2 is parity. And it's obviously mod P is in AC0P because this can be computed trivially by a single circuit or a single gate. And then there is the class ACC0. So this is the union of AC0M for all integers m greater than 2, including non-prime m. And so AC0P is separated from ACC0 by mod Q, where Q is not P. Then this is shown by Smolensky. So obviously mod Q is in ACC0 because ACC0 can have any kind of mod M gate. So this shows that giving more kinds of mod gates is strictly more powerful. And up to this point, we've been giving separations between classes using very simple problems. But then with ACC0, we don't really have any good lower bounds on it. We know it's contained in NC1. And in 2011, it was proven that NX, so non-deterministic exponential time, is not in ACC0. But this took a long time to prove. And so essentially, we have a very little idea how strong or weak ACC0 is. And this is for a constant depth class. So that's really a very striking result. Next slide. And then now on the upper side, we want to talk about what are the limits of NC, like efficient NC circuits. And this is a little tricky because we want to define it in relation to P to talk about the P equals NC problem. And we have to use a relatively weak machine to compute the reduction. And so two choices are common in the literature. A log space transducer, um, which is a machine that has log space, um, but can write to an output that's longer than that log space, and an NC circuit. And the former kind of reduction implies the latter, because as we saw earlier, L is contained in NC. Next slide. So the circuit value problem is the quintessential P-complete problem. And it asks, given the encoding of a Boolean circuit and its inputs, to compute the value of a given gate within the circuit. So think about the tableau construction by Cook-Levin, which converts the Turing machine on a specific input into a Boolean formula. In our case, it's a circuit. And previously we had used non-determinism to find a satisfying assignment, but now we just want to evaluate it deterministically. And so it's interesting that this is an interesting problem for our purposes because it kind of forces us to look at this like inherent sequentiality problem very straightforwardly, because it's asking, can polynomial depth circuits be evaluated by polylog, be approximated, or not approximated, but is there an equivalent polylog NC circuit for every polynomial depth circuit? And so the transformation from any P language to the circuit value problem, which encodes it, is highly local and can be constructed by a log space reduction. This can be seen, it's very similar to Cook-Levin, where the local state of each row only depends on a small local window. So to construct the circuit for this, you don't really need to store very much global state. You just need to know where you are, and that lets you index into previous rows of the construction. Next slide. And so we have strong reason to believe that there are problems in P which are not in NC, using the circuit value problem. And so Brondin gives the inclusion that for S of n greater than or equal to log n, depth of S of n is a subset of D space S of n. So if we could show that there is a language in P which has a space lower bound, or if we can show a space lower bound on the circuit value problem, that would show that there is not an NC circuit for them. And so the model of computation we use for this is the pebbling model. So you can think of having a DAG, which represents a circuit, represents the circuit, and you have a pebble representing when you store in a value. And so you start with pebbles on all the inputs, and you can pebble a vertex if all of its parents are pebbled in the DAG, representing you have all the values stored, and then you compute that value. And then you can remove a pebble to forget a value. And so this is a pretty broad and general kind of method for circuit evaluation. And it turns out that basically every kind of method for evaluating circuits actually falls under some variant of the pebbling method. Next slide. And so using super colliders, which are a type of graph, a DAG, we can show that if the pebbling method is the only way to compute circuits, then we actually have a separation between P and NC. Obviously, we don't know that the pebbling method is the only way, but it seems very natural. Next slide. So a super collider, as pictured in the previous slide, is a type of graph that requires every input to be connected to every output. And additionally, for every set of n inputs and n outputs, there has to be disjoint paths connecting the two sets of outputs. And so this forces some minimum space requirements because with the disjoint paths, every single one of them has to be pebbled during the evaluation of the outputs. And if you can show a lower bound on the number of pebbles needed to pebble, and when I say pebble, I mean have at some point pebbled every vertex on the graph, signifying that you've computed every node. And so if you wanted any particular node, you've computed it at some point. To pebble a super collider, we can prove a lower bound on the number of pebbles needed. And then we nest the super colliders inside each other so that in order to pebble a particular output in the outer super collider, you have to pebble all of its inputs and their inputs and their inputs and so on and so forth. And so nested super colliders give us a lower bound of n log n on the number of pebbles needed to compute certain graphs, which is way bigger than log k of n, polylog n. Moreover, given an n log n pebble budget, space budget, there is additional work that shows that you actually need exponential amount of total work. So we have strong evidence here for the separation between P and NC by the circuit value problem. Next slide.
Okay, so up to this point, we have seen that parallelism is powerful, but running many processes at once is not enough by itself. The real challenge is coordination. In many parallel settings, especially graph problems, lots of processes see very similar local situations. If they all follow the same deterministic rule, they can make the same choice at the same time, which creates collisions or causes the algorithm to stall. Randomness gives a clean way around that. Instead of forcing expensive global coordination, we let processes make independent random choices. With high probability, enough of these choices succeed with the computation makes progress everywhere at once. So the key idea here is randomness helps parallelism by breaking symmetry cheaply. Formally, this leads to the class RNC, which is the randomized analog of NC. Like NC, we still require efficient parallel computation, polylogarithmic time, and polynomially many processes. The difference is that the algorithm is allowed to use random bits and only needs to succeed with high probability or equivalently with bounded error. You can think of RNC as giving us a toolkit for problems where deterministic local rules are too rigid. Three recurring ideas are symmetry breaking, isolation, and sampling. For example, symmetry breaking lets processors avoid making identical choices. Isolation uses random weights to make one desired solution unique with high probability. Sampling reduces the problem size while preserving enough structure to keep working in parallel. We saw this question in the earlier slides. I'll just recall once. This connects back to the central question of parallel complexity. How much of efficient computation can actually be parallelized? We know that NC is contained in P because anything we do in parallel can always be simulated sequentially, but we do not know whether P is equal to NC. If the answer were yes, then every efficiently solvable problem could also be parallelized. If the answer is no, then some problems are inherently sequential. The strongest evidence against equality comes from p-complete problems like we had seen. These are believed to represent the hardest problems to parallelize because an efficient parallel algorithm for one of them would imply efficient parallel algorithms for all of P. At this point, a natural question is, why don't we just prove that some problems require large depth and separate P from NC directly? The obstacle is that strong lower bounds are extremely hard. We do not know how to prove lower bounds for restricted circuit classes such as EC0, and those results are very important. But these methods do not scale to general circuit models we would need for major separations like P versus NC. There is also a broader barrier from natural proofs, which suggests that many standard looking lower bound techniques are unlikely to resolve these stronger questions if common cryptographic assumptions hold. So the field faces two major linked difficulties. Proving strong circuit lower bounds is hard, and understanding whether randomness can be removed from parallel algorithms is also hard. So the big picture is this. Parallel complexity is a field with major algorithmic success, but its deepest theoretical questions remain open. We still do not know whether all of P can be parallelized efficiently. We still do not know whether randomness is fundamentally necessary for efficient parallelism, and we still do not know how to prove the lower bounds that would settle these questions cleanly. That is what makes the area so interesting. The algorithmic side gives us powerful techniques, while the complexity side tells us that we still do not fully understand the limits of parallel computation. That is pretty much what we had from our side. Thank you for your time.